Prestressed concrete beams. What exactly are they? How are they made? And why are they useful? Before we explain, it's necessary to provide a brief overview of traditionally reinforced concrete beams for comparison. Concrete is very strong in compression, but only 1/10 as strong in tension. So if we make a beam of pure concrete and apply a bending load, the top half gets compressed while the bottom half is in tension. This tension zone in the bottom half will form cracks that propagate until the whole beam fails. This is where reinforcing steel comes in. Primary structural bars are generally placed in the tension zone, so when the concrete cracks, the reinforcing steel takes the tension load. There are other types of bars, such as for controlling thermal effects, but that's beyond the scope of this video. It's also worth keeping in mind that the tension zone is not necessarily always on the bottom. For example, near a column or at a cantilever, the tension would be in the top and compression in the bottom. Traditionally reinforced concrete essentially combines steel and concrete and then lets it act as it would passively, compared to prestressed concrete, which actively engages the materials. Now let's contrast the traditionally reinforced concrete beam to a prestressed one. We'll look first at precast, pre-tensioned concrete. For this beam, first, the cables are placed in a form, and then they're tensioned. Next, the concrete is poured, and then allowed to cure. Once cured, the cables can be released from the tensioning forms. Now, the prestressed cables will contract. This induces compression in the bottom half as part of manufacturing, sort of like a cambering effect. Once the beam begins taking load, it still applies tension on the bottom half, but this time, the tension has to cancel out some pre-stressed compression before creating a zone of net tension. In this way, the pre-stressed beam is able to take more load than the traditionally reinforced concrete one, all else equal. The amount of pre-stressing has to be carefully calibrated to avoid tensile cracking on the top with too much pre-stressing, but also must be enough to avoid concrete shrinkage depleting the pre-stress over time as the concrete cures. Early pre-stressed concrete designs made the mistake of not properly accounting for concrete shrinkage. As concrete cures, the water inside it evaporates, and this causes shrinkage, which can occur for up to 18 months of curing. Let's examine how this shrinkage would impact our pre-stressed beam. As the concrete shrinks, so too would the pre-stressed steel bonded to it, which reduces the tension force in the steel, and thus reduces the pre-stressing load. So, in order to offset the losses of shrinkage, you need more pre-stressing. But, at a certain point, you'll rupture the steel if you pre-stress too much. That's where high-strength steel reinforcing comes into play. About 100 years ago, designers of concrete structures realized that in order to properly utilize high-strength reinforcing, it needed to be pre-stressed. This led to a lot of development in material science for high-strength reinforcing, as well as for high-strength concrete. Today, prestressed concrete generally uses both high-strength reinforcing and high-strength concrete in order to maximize the benefits of pre-stressing. We can't discuss pre-stressing without also discussing post-tensioning. Post-tension concrete is a similar active combination of concrete and steel, also generally using high-strength materials. But for post-tensioning, the pre-stress is applied on-site after concrete has cured, but before the structure sees its anticipated design loads. Post-tension reinforcing tendons are carefully draped throughout slabs and beams to achieve the desired bending and deflection criteria. Post-tension tendons can be either sheathed and greased or unsheathed, which have different benefits for load transfer, ease of construction, or replacement, and weatherability. But that's a deep dive for a whole separate video. The main benefits of pre-stressing generally stem from the fact that it actively engages the steel and concrete. This results in a stiffer section that presents options to use less material, allow longer spans, or carry additional load. Of course, these benefits come at the cost of added design and construction complexity, so use depends on the specific application. If this brief introduction to prestressed beams was interesting for you, let us know your thoughts in the comments. We also welcome your ideas for future video topics, and we're always curious to know what topics you'd like to see a deeper dive on. And, if you like these videos without sponsorship ads, consider buying us a coffee with the link below. We also appreciate every like and subscribe. Thank you very much, and see you next time.